Hi, welcome back to another video. Today we are covering another design problem, and this time we have to design an all-O1 data structure. So in this data structure, we have to store strings and their counts with the ability to return the strings with maximum and minimum counts. You might be thinking, why is this problem important? Why do we have to solve this problem? The learnings from this problem will help you to design complex real-world read-write systems. So it helps to develop the thought process, helps us how to think to solve complex problems. Reading the problem statement, we see we have to deal with strings and their counts. So the first thing which usually comes to our mind is we can use hash maps. So for our mapping, what we can do is we can have a string and its count integer, and this is a good start in developing our thought process. Using this map will help us to implement increment and decrement functions. And let's say we have a string abc and its count is 2. So if we need to increment it, we can check if it is already there and then we can increment it, and if you want to decrement it, then again we can check it and then decrement it. The thing which makes this problem complex is the requirement of these two functions, get max key and get min key. So if let's say we have multiple keys, and let's say I have another key def and it has a count of 4, and let's say another key xyz and it has a count of 7. So get min key should give us this string abc, and get max key should give us this string xyz. So we need some ordering of our keys. So if we just use a simple hash map, then we know that the keys of a hash map are not ordered and we will not get any ordering, and in that case we'll have to iterate over all the keys, and that would lead to O of n time. The next question we can ask ourselves is, can we do better than O of n? The answer is yes, we can do better than O of n. We can do this in O of log n time. For O of log n time, we can make use of a tree map. A tree map can have sorted ordering of keys. So how do we implement this tree map? There are going to be multiple keys with the same count. So for example, we have ABC here, which has count 2, and there could be another string, let's say K2, which also has count 2, and another string K3, which has count 2. What if we group all these strings with the same count together? Now this way the key in our tree map is going to be an integer, and the value corresponding to that key is going to be a set of string. So this way we can maintain a sorted ordering of our keys, and then we can get max key and min key in O of log n time, as tree map uses a balanced binary search tree using red black trees. If we don't want to use a tree map, we can make use of priority queue, and using priority queue we can maintain two heaps. So we can maintain a min heap and a max heap. These two heaps, min heap and max heap, are going to give us information about the min key and max key in O of 1 time. Along with these two heaps, we can use a map which has a mapping from string to integer. But there's going to be one problem. Now, what if we want to update the count of a random string in our map? So we can do that in our map using O of 1 time. But if we want to do the same update in our priority queue, then that is going to take O of n time. So to tackle this, we can use a concept called as lazy deletions. So I also discussed this concept in our previous video of max stack. I recommend you to watch that video as well to understand this better. So using this lazy deletion will help us avoid the headache of O of n updates. The question which might be running in back of your mind would be, can we do better? Can we still do better than O of log n time? So in the problem description, it says that we have to use O of 1 average time complexity. So can we do better than O of log n? And can we implement this in O of 1 time? I have some good news for you. Yes, we can implement this in O of 1 time. So let's have a look at how we can implement this in O of 1 time. To implement this in O of 1 time, one thing is sure, that we are going to need a hash map in some way, and And the hash map is helping us with add, delete and update operations in O of one time. And we have to think about how to implement the remaining two operations of get max key and get min key alongside these three operations, so that these all five operations work together and we can keep our data structures in sync with each other. For get max key and get min key operations, one thing which comes to mind is we need some ordering of the keys with respect to the key counts. So if the count is 1, then we have to group the keys which have count 1, and similarly when the count is 2, we have to group the keys accordingly, and so on. Now, which data structure will help us in implementing these two operations and also these three operations in O of one time? In our previous videos, we discussed about doubly linked list, and in a doubly linked list, we can create a new node, delete a node and update a node in O of one time if we get the reference to that node. To denote a doubly linked list node, we can create a class node, and inside of this class we can have a count and a set of strings which have that count. And we are going to need one more thing which will ensure O of one time operations, and that one more thing is we're going to need the mapping to this node in O of one time. To get the node reference in O of one time, we are going to need another hash map, and this hash map is going to have integer as the key and node reference as the value. So let me call it count to nodes. So this way, if an increment call comes in for string ABC, and if we are adding it for the first time, then in our counts map we simply add it as ABC1, and then in our doubly linked list we can create a node with this count 1, and in that node we can add this string ABC. When we are adding a string to our doubly linked list for the first time, we know that the count is going to be 1, and what we can do is we can add it at the head of our doubly linked list. So this doubly linked list is sorted based on the counts. So the lowest count is near the head and the highest count is near the tail. So the lowest count in our doubly linked list is going to be 1. So then we check if there exists a node already which has a count 1. So that node should be head.next, and if the count is 1, then that means that node already exists, and then we can simply add the string ABC to this node. And if it does not exist, then we create this new node and insert it between head and head.next. Now what if we want to update an existing key, let's say DEF, and initially the count is 4, and now increment call comes and we have to update its count to 5. So if this key was already present in our hash map counts, then that means that the node with count 4 was already present. Now the next thing we can check if this node with count 5 already exists in our doubly linked list or not. If it already exists, then we can simply add this key DEF to the node with count 5, and if it does not exist, then we can create a new node between this node 4 and 4.next. And final step would be we'll have to delete the key DEF from this node 4, and if the count of the keys in this node 4 becomes 0, then we can delete this node totally. We can delete that node from our doubly linked list and also remove that mapping from our count to nodes hash map, and also update this hash map with the new count for the key DEF. Using a similar approach, we can implement our decrement function as well. For get max key and get min key call, what we can do is for get min key call, we can simply check the head.next node and return any key present in that node. And for get max key node, we can check the tail.previous node and return any one of the keys in there. And this way we will have implemented our increment, decrement, get max key and get min key functions in O of one time. We can further optimize our space usage by merging these two hash maps into one hash map. So we can simply use a mapping from string to node and this will help us save some space and avoid repetition. Let's call this map as keys to node map, and let's try to figure out how we can implement our functions. So now we have a mapping from string to node, and let's say the string ABC comes in for the first time and we have to update its count as 1. So first we check if this string ABC is present in this hash map or not. So it is not present. Since the count of this key is going to be 1, we have to check the node which is next to our head node. So we check this head.next node and check if its count is 1. So if its count is 1, then it means that the node which has count 1 already exists, and we can simply add this key to this node. And if it does not exist, then we'll have to create a new node with this count and then add this string ABC to this set, and then insert our node between head and head.next nodes. And this way we will deal with the case when a string is added to our data structure for the first time. Now what happens if a string was already present, let's say def, and its count is 4, and now we increment its count as 5. Since the string def was already present, what we can do is we can do a get operation for this string def and get the corresponding node. Now we get the corresponding node which has count 4, and now we check if a node with count 5 already exists or not. If it already exists, then we can simply add the string def, and if it does not exist, then we can create a new node between this node 4 and 4.next. And once we do that, we can remove this string def from the set in the node with count 4. And if after removing the number of keys in this node becomes 0, we can also delete this node here. This way we can optimize our space usage and we can implement our functions in O of one time. I hope this made sense, and it will make even more sense once we write the code for this problem. So let's dive into the code implementation. For the coding implementation, we are going to need a hash map and a doubly linked list. So let's define our hash map. So we can define our hash map as map string to node, and let me call this keys to node. And before initializing our hash map, we're going to need to define our class node. So in our class node, we can define a count and a set of strings which have that count, and let's call this one keys. And let's also define the head and tail of our doubly linked list, node tail, and inside our constructor we can initialize our head and tail. So I can do new node -1, and then we have to also create a constructor here, public node, and then we can pass in the count, and I can set this dot count equal to count. And for the head and tail nodes, we are just setting the count as -1, and let's also initialize our tail node, new node -1. So we have to set head.next as tail. So since we are setting head.next, we also have to define a next reference and a previous reference in our node class. And similarly, we can set tail.previous equal to head, and we can also initialize our hash map, new hash map. And in our node constructor, let's also initialize the keys as well, new hash set. So this will initialize our hash set and it will have 0 keys. So for our functions, let's first create our get max key and get min key functions. We are going to get our max key at the node just before our tail node. So if the tail.previous node, if its count is -1, then it's an invalid node, or we can check if tail.previous is equal to head directly. So we can simply write tail.previous. If it is not equal to head, then what we can do is we can return any key present in our tail.previous node. So for that we use iterator, and then .next will give us any key in that node, and if it is equal to head, then we have to return an empty string. Instead of checking tail.previous not equal to head, we can also check if tail.previous.count is less than 1, then also this node is not going to be valid. Then also we can simply return an empty string. For simple cases, we're just checking if it is not equal to head. And similarly for get min key, we know we are going to get our min key in the node next to head. So we have to check if head.next is not equal to tail node, then we can return head.next.keys.iterator.next, and if it is equal to tail, then we can simply return an empty string and we will be done. For our increment function, the first thing we have to check is if this key exists in our hash map or not. So we can have an if check if keys to node does not contain the key, and we can have an else block. So for our if block, if this key is not present in our hash map, then what this means is we are adding this key for the first time. So what we can do is we can get the node which is next to head. So because we are adding this key for the first time, so the count of this key is going to be 1. So that is why we are getting our head.next node, because we're going to get the node with the least count next to head, and the node with the least count is going to be node with count equal to 1. And next we can check if node.count is not equal to 1, and then an else block. So for our if block, if node.count is not equal to 1, then that means that we don't have any node with count 1 in our doubly linked list. Then we're going to have to create a new node with this count. So new node equal to new node, and then pass in the count 1, and then we can add our key in this node first dot add key, and then we can insert in our doubly linked list. Insert in DLL. First we can set new node dot next equal to head dot next, and then head dot next dot previous equal to new node, and then we can set our head dot next equal to new node, and then new node dot previous equal to head. And after insertion, we can also insert in our hash map, and we can do keys to node dot put key, and then our new node. And if there is a node with count 1 already, then we can simply add our key to that node, keys dot add key, and then we can update the mapping in our hash map as well, key node. So this was the if check when the given key is not present in the hash map. For the case when the key is present in our hash map, first we can retrieve the node which this key maps to. So we can do keys to node dot get key, and then we can check the count. Let's call it current count equal to node dot count, and then we can remove this key from this node. And now if we check if a node with current count plus 1 exists in our doubly linked list or not. For that we can check the node next to this node. So node dot next dot count equal to current count plus 1. If it exists, then it's straightforward. Then we update our mapping key, and then we do node dot next, and then we can add this key to node dot next. And if it does not exist, then that means we'll have to create a new node. So we can do new node equal to new node current count plus 1, and then we can update the mapping keys to node dot put key new node, and then we can also add it to our new node dot keys dot add key, and now we can insert in our doubly linked list. So it's going to be new node dot next equal to node dot next dot previous. It's going to be equal to new node dot next is going to be equal to new node and then finally new node dot previous is going to be equal to node. And one final check before exiting the outer else block is if the original node that becomes empty. So after this call, if this node becomes empty, then we have to remove this node from our doubly linked list. So we can implement this remove function. So we created public void remove node, and then it's simply going to be node dot previous dot next is going to be equal to node dot next, and node dot next dot previous is going to be equal to node dot previous. And this way we are going to delete that node from our doubly linked list. And finally, for our decrement function, it is going to be straightforward. First, we can simply check if the key exists in our hash map or not. Then only it makes sense to decrement the count for that key. So in our if block, we can get the node which this key maps to. So node keys to node dot get key, and then we can check the current count. So it will be node dot count, and then we can first remove this key from our node. So first we have to check the current count. So if the current count is 1 and we are decrementing the count for the key, then that means the new count is going to be 0. So which means that we're going to have to remove the mapping from our hash map. So if current count is 1, then we can remove the mapping from our hash map. And if it is not 1, then first we can get the previous node to node dot previous. Then we have to check the count of our previous node. So if previous node dot count is equal to current count minus 1, then that means that the node with current count minus 1 already exists, and we just simply need to update that node with that key, and also update our hash map mapping key comma previous node. And if there is no such node which has the count as current count minus 1, then we are going to have to create a new node in our doubly linked list. So for that we can do node new node equal to new node current count minus 1. Then we can add that key to our new node dot add key, and then we can insert it to our doubly linked list. So previous node dot next is going to be equal to new node, then new node dot previous is going to be equal to new node dot next is going to be equal to node, and then finally node dot previous is going to be equal to our new node. And then we can update our hash map mapping as well. Dot put key new node. And finally, before exiting the outer else block, we can check if the set becomes empty. Node dot keys dot is empty. We can simply remove that node. So I hope this made sense. So let's try to run it and see if we did any silly mistakes. So yeah, that got accepted, and let's try to submit. To fix this error, we forgot doing a cleanup in our decrement function here. For this if check, we do not call this remove function if the node dot keys becomes empty. So instead of if being here, it should be outside of this one. So if we have it here, and now let's try to run it. So this got accepted, and let's try to submit. So yeah, that works, which is great. So I hope this made sense and you got a better understanding. And if you have any doubts, please let me know. And I highly recommend you to draw diagrams to understand linked list problems better. And thanks for watching, and I'll see you in the next video.